Hi, in this video, we want to take a look at estimating autoregressive moving average models using method of moments. All right, so in method of moments, what we're going to do is that I have a collection of parameters that I want to estimate. I also have a collection of statistics that I can compute using my observed data. Now, we have a functional relationship between the two of these between the expected value over here and the parameter I want to estimate. So what we're going to do, I'm going to take my data, I'm going to pretend that the statistics I get are exactly equal to the expected values. Then what I'm going to do, I'm going to drop it into that functional relationship, and we're going to use what I get to estimate the parameters I'm interested in. Now, think about an autoregressive moving average model. All right, I'm going to have several coefficients to think about. I'm going to have the autoregressive coefficients. I'll also have the moving average coefficients to estimate. We want to figure these out. All right, so now as we work through this, we're going to take examples from time series analysis applications, chapter 3. Here are the name of the authors. Here is their GitHub page. And UCF students can download this textbook for free through the library. All right, so now let's get into it. All right, so what we're going to do is we're going to take our data and we want to estimate an ARIMA process, so autoregressive moving average. Not going to worry about integrated yet. And we're going to go ahead and we're going to take the point of view that we know what the degrees are, the P and Q, the degrees of our autoregressive moving average model. So we know the degree of the autoregressive part, we know the degree of the moving average part. Now, in another video later down the road, we'll talk about how to estimate P and Q. But for now, just take the point of view that we know what these are perfectly. Okay, so what we want to do, we want to estimate the coefficients in the autoregressive portion. We want to estimate the coefficients in the moving average portion, and we want to estimate the variance of our white noise process. Okay, so what we're going to do, we're going to identify statistics whose expected values have, as a group, have a mathematical relationship with the desired parameters. And then I'm going to take those statistics that I compute, I'm going to treat them as if they're exactly equal to their expected values. I'm going to drop them into that mathematical relationship, and what I get out is going to give me an estimate of the desired parameters. Okay, and so something about this is that we're making a lot of theoretical assumptions as we work through this, but this works out pretty well. Now, something that must be pointed out every single time we use method of moments is that this can lead to suboptimal estimators in several different ways. And so one aspect is the fact that we can really get, compared to alternatives, when we have multiple choices, method of moments tends to give us like more variance on the estimator than maybe maximum likelihood. Also, something that can happen is that with method of moments, we can get an estimate that isn't even in the parameter space. So let's say I know I have to have a positive number, theoretically for the estimate. It's possible that I get a negative value. In fact, in this video, we're going to look at an example where we know that the parameter has to be a real number, but potentially, depending on my data, we could end up getting a negative value. And that wouldn't make sense. Or sorry, not negative value. We'll get a complex number, a non-real number, when we know we need to be keeping it real, yo. Okay, so it's something that can come up with this. Personally, I usually use method of moments when I'm using other techniques that are iterative in nature. And I'll use method of moments for the initial values to kick off the process, because usually it's not too bad of an estimate to start out with. Another case of using method of moments is when we don't have other alternatives, when no one has figured out the maximum likelihood estimate or another technique, or maybe it's just not wieldy. If I wanted to take the academic paper and write out the code, I just need something here and now. So, there are times to use this, and it's good to always have in your back pocket. All right, so now let's talk about the Yule Walker equations. All right, so let's go ahead and let's just focus for the moment on a strictly autoregressive process. So I have x of t is equal to the coefficients times the lagged values of our data plus our white noise term. Okay, now here's what we're going to do. I'm going to multiply both sides of that equation by a lagged variable or a lagged value. And then I'm going to take expected value. When I do that, I'm going to get equations for different lags on what I multiply with. All right, so what we're going to do, I'm going to take a lagged value of x, multiply everything by it, like this. Then we're going to go through and start taking expected values. So here, take expected value. Here, I take expected value, all the way down to the end. Then notice that here I have, in this expected value, I have the white noise term times the lagged value. All right, so this one is going to give me different values depending on the lagged value of x. So if depending on what we put down, we'll get different values. And so what we're going to do is we're going to have two situations. When h is equal to 0, I'm going to see that I'm going to end up getting this equation. Notice that I've got gamma of 0, and I'm subtracting all of this business. So I have the autocovariance at 0, which is the variance, which I'm getting from over here when h is equal to 0. And then I subtract off everything else, gives me this. And then this term here ends up being equal to sigma squared. Now, when h is not equal to 0, when it's 1 through p, then I'm going to have the autocovariance at h is equal to an equation on the lagged or less lagged autocovariance values. All right, now, if I look at this, I'm going to have p plus 1 equations off of this. All right, so now I've got a system of equations. Let's go ahead and do some matrix algebra. All right, so what I want to do, if I'm doing matrix algebra, I want to express this as a matrix. That way everything is faster, easier, shorter to write out, and I'll do exactly that. So when I look at this, I'm going to let gamma sub p be the autocovariance matrix. I'm multiplying by the vector of coefficients, and this needs to be equal to the vector of autocovariances. So we have autocovariances in two spots in here. We have in this matrix, but also in this vector. And that comes from this setup here. Now we also, if I write this out, we have that our variance is going to be equal to the autocovariance at 0. So this is the variance of the white noise. This is the variance of the time series minus the dot product between the coefficient vector and the vector of autocovariances. Okay, so now I have a system of equations. I can work this out. So the big idea here is now solve, because I've got an estimate for these values from my data. I've got an estimate for these values. If I multiply both sides by the inverse of big gamma sub p, I'm going to get an estimate of the coefficients. And so to fill this out, to get everything, to get an actual value, so at this point, everything is just the theoretical values. What we're going to do, I'm going to estimate these values using my data. I'm going to estimate these values using my data. And so I do exactly that with the standard formula. Now, technically, this is a biased estimator, but it's an estimator. We'll run with it all nonetheless. And so then I'm going to just run through the process. So I estimate the gammas. So that gives me an estimate of the matrix of gammas and the vectors of gammas, a lot of covariances floating around, which this equation here with using the inverse gives me an estimate of the coefficients. And then I drop this estimate into this equation, and I know that this is equal to that. So I have to rewrite it in this format. And so now, boom, I've got an estimate of my white noise variance. And so this gives us what we really want. So now, to actually get the Yule Walker estimators, we're going to, instead of using covariance, we're going to use correlation. So I'm going to use auto correlation instead of auto covariance. Conceptually, it's really the same thing. I'm just doing a little bit of tweaking here and there. I'm estimating just like I would. It'd work out either way. So now, when the sample size is large, the Yule Walker estimators are going to be approximately normally distributed, and the variance estimate is going to be close to the population variance. Now, something that I said earlier, I forgot to mention this point I'm about to say, is that when I get wonky values out for method of moments, I usually have a small sample size, or I have a poor model for my data for the situation I'm dealing with. Probably both. Every time I've seen problems with a method of moments estimator, I've had small data in real life. And so just giving you a heads up that if I have small data, there really isn't a whole lot I can do in a lot of situations anyway. But more than likely, maximum likelihood estimator will give you a better estimator if it's available, if it's realistic for the situation you're in. All right, so now let's go ahead and talk about what do we get when we look at the large sample aspects of the Yule Walker estimator. So let's go ahead and say that I have a lot of data to work with, and potentially just think of as much data as I could possibly want I've got. So we can start thinking about things asymptotically. All right, so the asymptotic behavior of a Yule Walker estimator is when we have a strictly autoregressive process, is that we can see that these coefficients are going to converge in distribution to the true value subtracted off, multiplied by the square root of n, and the distribution of that is going to be in distribution convergence normally distributed with this variance here. And we can see that our estimate of the white noise variance is going to converge in probability. All right, now the proof, I've actually done the proof already. It's already posted on my YouTube channel. It's pretty juicy. It's a good long proof. Check it out. It's there for those who are brave and willing to dive into theoretical statistics. All right, so now the Yule Walker estimators are presented pencil and paper wise using an inverse of the covariance matrix. Well, you know what? That can be unwieldy. If I have a large P, a large sample size to work with, like the degree of my autoregressive process is pretty big, and I've got a large data set to work with, that matrix equation may not even fit inside my computer if it's big enough. I can't even get it to compute. And so instead, if I'm in that situation, we'll use the Durbin-Levinson algorithm to estimate the coefficients without ever doing a matrix inverse. I won't actually have to explicitly write out the matrix presentation, but I need to write it down pencil and paper so that I know how to drop this into the Durbin-Levinson algorithm. All right, so we're going to take an iterative calculations, and we're going to estimate consecutively the values of our coefficients. And so if we apply large sample results for the Yule Walker estimates, assuming that things are converging, everything's behaving the way we want to, we're going to get a large sample distribution for the partial autocorrelation function phi sub HH. All right. So there, when H is decently large, we want this, pretty big compared to P, we know that the square root of n times that partial autocorrelation function estimate will converge in distribution to standard normal. All right, so that gives us the ability to run hypothesis tests. So anytime I know the distribution of something, I can run hypothesis testing, because once I have a distribution, even if it's only an approximation, I can get a p-value. If I can get a p-value, I can get, I can make a decision on to reject or fail to reject a hypothesis. All right, so let's run through an example. Let's run the Yule Walker estimates for a degree 2 autoregressive process. So let's go ahead and say this is my actual process. So I've got 1.5 times the previous value minus 3/4 times 2 values back plus the white noise term. And we're going to say that the white noise term is Gaussian with a standard normal. All right, so let's go ahead and run through the example. Here, I'm just setting up, what is my observed data sample size. Here, this v sub x is going to be the vector holding the x values. Here, I'm setting seed, so I can repeat this later down the road. And now I'm just going through the process of taking the previous values that I've had and getting the values I want for the next one. And so something to notice is that I went ahead and just said x sub 1, x sub 2 are equal to 0, because notice I have to have at least 2 points to be able to get the first one as a completely random value on there. And so I just kicked it off 0, 0 to let it run. And here is our overall variance of 8.6 about. And so here we can look at the autocorrelation function. And here I chopped it off at 2 because we know that's going to be 0 past that, because we know it's degree 2 from how I built it. Here we've got those autocorrelation values. Here we can look at the autocorrelation values here and the partial autocorrelation over here. Notice that it cuts off as it should when we're dealing with strictly autoregressive process. So here are our estimates. All right, so now we're going to manually estimate model parameters. And so note that the time series was generated using random number generators, and the estimated values may change with different runs. So, when I was preparing for the video, that was a different calculations because of the random aspects to it. So things may be a little bit different in the actual code output than the text I typed out. Please just know that's from random number generation. And so here we're just going to go through and manually calculate it out. So here I get just a little bit greater than 1.5. Here I get just a little bit less than negative 3/4. Okay, so I mean, right off the bat, that's pretty close, right? So that's not too shabby. Now here, when we do that variance estimates, we know that it's supposed to be 1. That one could do a little bit better, but that's not too far off. It's in the right ballpark. And so here we can estimate the variances for the purpose of like a confidence interval. And so here I've got that covariance of the coefficients going on. Now we can also estimate this using a function built in R. So here, this is the ordinary least squares estimate of an autoregressive model. Here I'm saying there's no intercept, and don't subtract off the mean. And so here we can see that we actually got a little bit better of an estimate all the way around. So here, the authors of R, use some more material, some more academic papers to improve the autoregressive ordinary least squares estimate, but we're still close. So this shows that in general, if you don't know, don't compute it manually. Let the function do it for you. All right, so let's go ahead and try this process on the recruitment time series from the ASTSA package. First thing I'm going to do, I'm going to clean my workspace, make sure there's no junk floating in there, make sure that anything I've used previously doesn't get misunderstood in my computations. I'm going to set my output out to 2 digits, and I'm going to try to avoid scientific notation if I can, and I load the data from the package. So now, from a previous video, we already established that we feel that this should be a degree 2 model. Let's go ahead and fit it using that ordinary least squares. And we can see we get 1.35 and negative 0.46. And here it estimates an intercept. I could go through and drop that. Here is the Yule Walker version of that same OLS function. And you can see that we get slightly different values here, but they're close. They're in the same ballpark. So here we can see that this is both of these are smaller in magnitude. Notice that here this is positive and this is negative. And when I get slightly smaller values, they're like the amount of change here is comparable to the amount of change here. And that don't be surprised if you see that in real life, because things are kind of like balancing. These two are kind of balancing each other out on this. So now, if we want to estimate standard errors, I'm just going to take the variance of the coefficients from our Yule Walker estimate, take the diagonal, and then the square root, and this will give us our standard errors. So about 0.04. And here's the variance of our predictions. All right, so now let's go ahead and obtain the 24-month predictions and their standard errors and plot those results. So here I'm using the predict function to get 24 months ahead. Here we're using the standard errors to get an upper and lower bound, just one standard error up and down. And we're going to use the time series plot to look at it. And then we're going to put down the predicted values with the upper and lower values from the standard errors on there. And so now we get, here's the plot of the original data over here in black. Here is the estimated values, and up and down, one standard error. And notice that this is going to flatten out. That is how it should be. This is going to flatten out, and it's just going to, just stay there if we keep on letting it predict further and further and further. All right, so now the Yule Walker estimators are optimal for an autoregressive model in the sense that the asymptotic distribution is the best asymptotic normal distribution that we can get. And when we say best, we mean least variance. This is because given the initial conditions, the autoregressive model are linear models, and the Yule Walker estimators are essentially least squares estimators. So really what we're doing, we're extending regression to the lagged variables and the current value of our time series. If we use method of moments for moving average or autoregressive moving average models, we will not get optimal estimators because such processes are nonlinear with respect to their parameters. All right, so that's a lot of words. All right, so what we're saying is the Yule Walker are really good for autoregressive models, but they're not as good for moving average or autoregressive moving average. Now, let's go ahead and run through an example with a moving average 1 model. Now, this is as simple of a non-autoregressive model that we could come up with, a moving average 1. I mean, that's as simple as it could be, but we're going to see that some things can go off the rails with method of moments. Usually in real life, when it goes off the rails, either I have a poor model for the situation I'm in, or I have very limited data. My experience is it's usually very limited data. All right, so let's say that we have a moving average 1 time series where we have the current white noise term plus a coefficient times the previous white noise term, and that coefficient is less than 1 in magnitude. All right, so let's go ahead and compute the variance, autocovariance, and autocorrelation of this process. All right, so from this structure, if I know that x of t is an MA1 model, I immediately know from the pencil and paper calculations that this is going to be the variance of x. This is going to be the autocovariance of 1. And here, this is the autocorrelation of 1. Okay, so now look at this right here. I have a relationship between autocorrelation of 1 and the theta that I need to estimate to get to this equation. All right, so if I can figure out what this theta is, I have a model for my entire time series. So what are you going to do? If I knew this value here, I could use the quadratic equation to figure out what theta was. Okay, so what we're going to do is I'm going to estimate the autocorrelation, and I'm going to pretend that my estimate is exactly what it's supposed to be, and then I'm going to set it equal to the equation I have over here, and then I'm going to solve. All right, so here we do exactly that. Notice I put a hat on the theta. Now, if I go through and do the college algebra of this, I know that this estimate of the coefficient is in fact going to be something using the quadratic equation. And this part is just using, college algebra, mathematics, simple stuff. All right, so now let's check out this. Look right in there. If I check that out, you'll notice that if I have an autocorrelation greater than a half, if it's greater than a half in magnitude, then I'm going to get an imaginary number on this part of the quadratic equation. And so that doesn't make sense for what's going on. If I'm using real numbers, they're coming in and I've got white noise process as standard normal, it doesn't make sense to get complex numbers. So I know, so this is a good example of method of moments really not being that great for the situation. So here, I need to be in a theoretical situation where autocorrelation is less than 1/2 for this model to make sense. Otherwise, this part goes off the rails. All right, so now there's a further problem with this in that using the quadratic equation, I'm going to get 2 solutions. I have to pick one. I have to know which one I want to use. All right, so if I go through and I consider plotting out what we've got, when we use addition, we're going to get a vertical asymptote when, so if I put a plus sign here and I start considering what happens when this is equal to 0, then I'm going to get a vertical asymptote on this function here. Now, if I put in a negative sign and I plug in 0 for my estimate of the autocorrelation, it's 0 is still outside of what can be put in there, but the discontinuity is just a hole. All right, so if I take the limit one more time, we're taking it to the limit one more time. Now think about 0 for here and here. In one situation, if it's a plus sign, taking the limit as the row goes to 0 with a plus sign, I'm going to get a vertical asymptote. And I don't know what to do with that. But if it's a negative sign, and I take the limit as row goes to 0, I get a hole for the discontinuity, which means I can just treat the value as if it was equal to the limit value, and that's a much better way to go. So we're going to go ahead and exclude the plus value from our estimate. And so now this gives us a value. But that was a pretty complicated process to get to this, right? We had to be mindful of what the limits are with respect to row as row goes to 0. And so now, just to demonstrate to you that if I do the plus sign, so here, theta sub p is when we're using the plus, theta sub m is when I'm doing the minus, we can see that we get a vertical asymptote around 0 for the autocorrelation of 1. And here we have a hole in the discontinuity. We'll just get a missing value, and we take the limit from the left as the right as the value if my estimate of rho is equal to 0. And this is a much more reasonable value to be working with, because here, a little bit greater than 0, I have a super high value of theta. A little bit less than 0, I have a super low value. That means it's unstable with respect to my data. So I really don't like that to work with. So I'm going to go with this one for my estimation. And we can see that rho goes from negative 1/2 to positive 1/2. Now, something that we can do, we can invoke the delta method. And now this is a pretty complicated presentation, and the delta method can get kind of hairy. I'm not going to go any deeper into the delta method in this video because it's long enough as is. And in fact, this variance can be simplified a little bit. I did it by hand, pencil and paper, but I didn't put it in the video. I just left it the way the authors had it. And this is just saying that this theta hat is going to be asymptotically normal for the expected value we want it to be, and this term for the variance, which we'll notice that the variance will get smaller and smaller as n goes to infinity. Now, I want to highlight the disadvantages of the delta method for this particular problem, this MA1 model. If that auto correlation of lag 1 is greater than 1/2, we were going to get complex estimators, and it doesn't make sense for our process. There are two solutions, and so we had to figure out using calculus and limits to figure out which one was the better one. One of these was a vertical asymptote. So if I made the wrong call on this, I would get an unstable estimator. One would be going off to positive infinity, one would be going off to negative infinity. If I just had a little bit of bump in the auto correlation, if it was around 0. And in general, most of the time, method of moments will have greater variance than maximum likelihood estimates. So in general, most of the time, we want to use maximum likelihood instead, but there are times that it's just not available. Or maybe it gives us a result that we don't trust, and the method of moments, we look at it and we feel better about it. So we want as many tools in our tool belt to work through this. All right, so let's go ahead and run through an example. Let's say that I've got 0.9 for that coefficient of the moving average, and let's run some simulated data. Here I'm setting the seed to make this reproducible, and I'm just going to generate n data points, and let's go ahead and compute that autocorrelation function. Here's my autocorrelation. Let's plot the ACF. And we can see it cut off pretty fast because we know that makes sense. All right. Well, that's all I've got for you. Life is short. Do math.